This episode of the HVAC School Podcast is made possible by generous support by Testo and Carrier.
You know, the sort of bloke who walks up to you in a bar, sits a little too close, and then starts talking to you. You try to ignore him, but he doesn't take the hint. He starts in about total nonsense. Like you know what he's talking about. Stuff about enthalpy lines and Mollier diagram. Well, that's Brian Orr.
Yes. All of it is true. I am Brian, and this is the HVAC School Podcast, part of the HVACRschool.com family of products for the service technician community. And today we have our regular contributor, Jim Bergmann. I hope he remains a regular contributor, and I think he should, just so long as I'm able to hang on to that little piece of blackmail that I have on him. And Jim's going to talk about one of his favorite subjects, which is evacuation. This is going to be just one piece in a large conversation that we're going to continue to have about evacuation. So we don't hit everything, but we hit some of the high points. And this episode is long enough as it is. Another thing that I was able to get my hands on was a recording of Jim speaking to a technician recently.
I don't know who you are. I don't know what you want. But I will find you and bore you to death about vacuum gauges and core removal tools.
All right, so we are recording.
What are we going to talk about this time?
This time we want to talk about evacuation, I think. That's sort of an easy one for you, sort of a softball, don't you think?
Yeah, that one sucks.
You don't like it?
No, evacuation sucks. Whatever you want to talk about.
Let's do evacuation, though, because I think evacuation, first of all, it's, if I'm counting correctly, I think it's the most popular video you've ever done is your video on the, 52 seconds to 300 microns or whatever it was. What was it?
Yeah.
500 microns, yeah. Which is a video that I watch just to put me to sleep at night because it's so compelling.
I thought it was the wind noise in the video that made it so good. So
yeah, it was, the wind noise was good. The music, the only criticism that people seem to have was the music and the wind noise. I like the music. I have to keep my role here as the consummate brown noser of Jim Bergmann. It was a great video because it demonstrated something that I think technicians do spend a lot of time on, which is evacuation. And there's sort of this feeling, I guess, among a lot of techs that getting a really good vacuum, say getting a 300 micron vacuum is near impossible. I remember that was the case when I started rolling out micron gauges at the place that I worked before I started my own business, which I guess I'll start by telling this story real quick. The year would have been probably 2002 or 2003, probably 2002. I was really hammering everybody to use micron gauges, and we had an issue where we had lots and lots of wet systems at this company that I worked. It's an enormous company, and they did lots of new construction, and I was in charge of hiring and training new technicians, and a lot of what my new technicians were doing, the guys who worked for me, were doing startups on these new systems, and we were running into all kinds of wet systems. And what we found out was there was two reasons that they were wet. And of course, this was also when 410A started really becoming the thing. And so we had all these, issues with compressors blowing up and shooting black oil all over the place. When I say blowing up, I mean blowing a terminal. So it's pretty extreme. And what we found out was one was that installers were pushing copper line sets through chases, PVC chases, with nothing but the plastic caps on them. And the caps would, of course, fall off, and then there would be water laying down in the chase, and then they'd basically just jam this whole line set full of water. So that was one reason why we were running into lots of wet systems. And then the other reason was part of the installation protocol was to cap and fill the drain lines to make sure that the drains didn't have any leaks, because we had a lot of second-story air handlers with fairly long drain lines, and they wanted to make sure that the drains didn't have any leaks, which, is a good practice. Initially, when they would rough in the drain in the copper, they would cap it and fill it with water. That was how it was designed. Well, they had some installers who weren't the best with English, and when they told them to cap and fill the lines with water, they thought that meant the copper lines.
Oh, no.
So there was entire subdivisions where they were capping the copper, pinching it and sealing it off, and then filling it with water. And I won't tell you what this company ended up doing about this because it's not what should have happened, but we were running into a lot of wet systems is what it came down to by the time we got there for startup, which is after trim, after the equipment had been set, and we would show up, just wire it up and do the run test and commissioning. And so because of this, I said, look, we absolutely have to make sure that everybody has micron gauges, because up to that point, nobody but me and a couple senior techs had them. And so we made it mandatory and provided a method for everybody to buy these vacuum gauges. And they bought I think they were Supco Supco or Robinair, I'm not sure which, but they had the little LED lights that would kind of go off as they went down the scale. And so it was it's sort of a loose approximation of what it is, but it would just kind of go off as they went down. And we rolled them out the first week, and the first week we didn't hear much. And then the week after that, essentially every single person brought them back in and said they don't work anymore. And what we found out was, based on how they were positioning them, and I learned a lot through this as well, that they were shutting their vacuum pumps off, without valving off properly, and the vacuum pump oil was getting sucked into them and laying down in them, and they were just getting all contaminated. And so through that, I learned that not only do you need to use a vacuum gauge, but you need to follow a lot of other practices in order to make sure that you don't have a mess on your hands. So that was a really long story to introduce the sort of optimal way of evacuating and kind of why we evacuate in the first place and what other considerations we have when we're evacuating. So that was just me teeing up the ball there. And so now you can hit it from there.
Well, thank you. That was quite painful for me.
What, hearing the mess that we had in our hands?
Yeah, hearing about refrigerant lines being filled up with water just makes my skin curl.
The only acceptable repair for that would have been to
take out the lines.
The refrigerant lines, right?
Yeah.
Yeah, and that's not what happened, and I digress.
Well, this kind of stuff happens more than we care to think. Probably the best place to start with this is your evacuation rig. We honestly, as an industry, I think there is nothing that we have forgotten more or never learned. I would say not even forgotten. I say never learned is the science of vacuum and evacuation. It is a crazy science, and it doesn't work like anything that you would anticipate. So there's got to be some things that, as we talk about, we'll try and explain them in a way that people can get this, but it's a very, very interesting science, and it's one of those things in textbooks, they're so lacking, it's ridiculous. If somebody wants just a good primer on this after we're done, there is a page I wrote years ago. It's at TrueTech Tools. If you look up evacuation training or vacuum training on TrueTech Tools, you'll find it. It's a good primer to this. I'd highly recommend, if you haven't gone to that, it's there. I think Brian also put a link out on one of his Facebook pages. If you dig around, you might find it there too at some point. Let's start with an evacuation rig. Probably the most important thing is don't ever evacuate through quarter-inch hoses again. All right? It is a absolute waste of time. I've got a book, and I'm trying to find the title of it here, see if I have it sitting on my desk here. But I think it's called Review of Vacuum for Service Engineers. It was written in the 60s by a thermal engineering company. I don't have it sitting here, so I hope I got the title right. They talk about the conductance speed of hoses, and I'll talk about that in just a minute. But one of the things they talk about is the conductance speed of a quarter-inch hose is so low that we're not even going to discuss it because it's not even worth talking about for evacuation processes. In other words, they're saying, who would use a quarter-inch hose for evacuation? Yet, as an industry, that's pretty much all we use, okay? In my past life, I've worked on some digital gauges, and one of the things that people have always said is, oh, yeah, I'd love to have a micron gauge built into my digital gauge set. And in fact, I got chastised for that because when I built one of the sets, I didn't have a micron gauge in there. And it's like, well, why didn't I have a micron gauge built in it? It's like, because the marketing department doesn't run engineering. That's exactly why. Because number one, no quarter-inch hoses. Number two, get rid of the manifold. Well, why do we say these things? Well, let's start with this. Why do we have them to begin with? Well, why do we have them to begin with is because we use quarter-inch pressure test points on an air conditioning system. So when we hook up that hose, that quarter-inch line was meant to be a pressure test line, not an evacuation line. When you think about atmospheric pressure, the lowest vacuum you can pull is negative 14.7 PSIG, 29.9992 inches of mercury. As many nines as you want to put on there, it just keeps going down and down and down and down. In our industry, actually, we don't even do deep vacuum. We get into what they call as roughing vacuum. We're just simply trying to remove atmosphere, air, and water out of the system. So when you get into semiconductor industries and vacuum tubes and things like that, these guys hit vacuum levels that are completely unattainable by the equipment we use. They use things like turbomolecular pumps and things that probably move 10 times the amount of atmosphere that we're removing with the equipment that we use today. So I digress for a second. But if the deepest vacuum you can pull is negative 14.7 PSIG, right? That's the limitation. It's a physical limitation. You can't go deeper than that in vacuum.
So I think some people are going to ask, well, why is that the deepest you can go? And the reason is that that's the pressure of the atmosphere that exists around us. That's
right.
Vacuum in the way that we often think of it, like it's sucking. Our heads are kind of messed up about that in the first place. Really, we're reducing below pressure that exists. 14.7 is the pressure that's exerted on all of the surfaces at sea level, and that does change depending on where you are. Sea level and even barometric pressure can affect that, based on my understanding. But we can only pull down to where you've negated that. You've removed the atmospheric pressure down to zero. You can't go any below that.
It goes back to this. We always talk about space being a vacuum, right? And if you're out in space, between here and the moon, that's as perfect of a vacuum you can get. There's nothing in space. It's void of any oxygen, any atmosphere, anything. So how does our atmosphere work, right? Well, we got this globe, the Earth, and it's got this atmosphere that's around it. You got this suction of space pulling that atmosphere away from the Earth. Well, what holds that atmosphere in is gravity, right? We have gravity that's pulling this atmosphere in, and the closer it gets to the Earth, the stronger the gravitational pull is. So at sea level, we have our highest atmospheric pressure, and if we go up on the top of Mount Everest, the atmospheric pressure drops because air has weight, air has mass, and air being primarily oxygen and nitrogen, primarily nitrogen. That mass is what we're removing. We're taking the atmosphere out of the refrigeration system. So the only thing in the refrigeration system left is refrigerant and oil. We want to remove all the atmosphere, all the moisture out of that system so that just refrigerant and oil are circulating in the system. And so when we talk about, again, what is the highest atmospheric pressure we can get? It's negative 14.7 or 14.7 PSIG is our atmospheric pressure. We commonly consider that 0 PSIG. Or if we were using an absolute gauge, the gauge would say 14.7 PSI. And if we pulled a vacuum on an absolute gauge, it would go down to 0 PSIA. If we're pulling a vacuum on a compound gauge on a pressure gauge, it's PSIG, it's now negative 14.7 PSIG, right? Or just in different units of measurement, 29.92 inches of mercury. It's just a different scale that gives us a little bit higher resolution. And then you can take another scale, the micron scale. There's 760,000 microns at atmospheric pressure. And we're taking it down to, 100 microns, 200 microns when we're doing a proper evacuation. So these are just different scales, but they're all the same thing. So let's go back to that hose for just a minute. And this is a question I'm going to ask you, Brian, just to put you on the spot because you need to be on there once in a while. If the deepest pressure that we can pull is negative 14.7 PSIG, what is the only way that we can increase the flow?
I don't even know if I understand the question properly, but I'm going to say by increasing the volume.
You're on the right track there. But okay, if we're to blank off our vacuum pump, the pumps can achieve negative 14.7 PSIG, right? Just roughly, that's what the pump can pull, okay? If we want to increase the flow, if the limiting factor is the pressure on a line, how can we increase the flow and turn the volume of gases going through that hose? Don't you have a cricket sound effect at this point? Chirp, chirp.
Yeah, hold on. Let me see. No, I don't have crickets. I have this. It's not working. This doesn't really work. No, this doesn't really work. I need anything to distract from the fact that I don't have the answer to this question.
All right.
So go ahead.
You have to increase the hose diameter. It's the only way to increase flow is to increase hose diameter. If we have a 1/4-inch hose with 14.7 PSI behind it, and we have a 1/2-inch hose with 14.7 PSI behind it, of pressure, right? And we're squirting water, which hose is going to emit more water or more gallons per minute if they're both at the same pressure?
Okay, right. I get it. So the larger hose. Yeah, I understand. Because the pressure can't be changed. It's not like you can put a bigger pump on it and create, more pressure differential. It's limited in that way. The only thing that you can do is change the diameter of the hose to a larger diameter.
That is correct. And you have just discovered the most fundamental important part of evacuation. Pump size does not matter. It really is secondary to what you attach to the pump. When you have a 10-foot or 1/4-inch hose and you have a Schrader core in the line, you're pulling about 0.7 CFM through that pump, no matter how big the pump is. If you have a 3 CFM pump, a 5 CFM pump, and a 7 CFM pump, because the most pressure that pump can develop is negative 14.7. The limiting factor becomes the evacuation rig that is attached to it. So if you're using 1/4-inch hoses and you're not pulling out Schrader cores, you may as well have a 1 CFM pump. Because if you put a 15 CFM pump on there, it's not going to happen any faster. We're bound by physics, and this is what everybody forgets. Manufacturers of pumps even forget this. How many manufacturers, it's very interesting. I'm going to give Appian a little plug here because they were the ones that really reintroduced the industry to oversized evacuation hoses, right? Dave Boyd discovered this in Thermal Engineering's catalog. Thermal had written it back in the 50s, 60s. I think it was a book Dave's dad had. And Dave really reintroduced the industry to this. And it was some things, my father always knew this. I think it goes back to I was listening to one of your podcasts earlier with Dan Houlihan, who was the guy that he said, "Why did you do this?" He goes, because I've always known it, right? And it's like, that was sort of the way my dad was. My dad always used oversized evacuation hoses, but my dad did chillers, 700 tons and up. And I'm like, I figured, well, you do big chillers, you just got to have big hoses. But he did that because it would take a year to evacuate a chiller through a 1/4-inch hose, right? Because at 0.7 CFM, you're never going to get the job done. But going back to this for just a minute, the evacuation rig is by far the most critical element of attaching your vacuum pump to the system. So the first thing you want to do is, number one, eliminate the manifold completely. You do not want to have a manifold gauge system attached to the system when you're doing the evacuation. You need to, first of all, attach it with core tools. Core tools simply allow you to remove the Schrader core. The Schrader core is a restriction. We're going to take those core tools and we're going to take the cores out, set them aside. We're going to attach that vacuum pump with 2 either 1/2-inch hoses are ideal. You could go with 3/8, but 1/2-inch hoses are ideal. You're going to attach it with 2 1/2-inch hoses, and you're going to attach that directly to your vacuum pump. We want to be able to use the core tools to isolate the evacuation rig from the system, from the refrigeration system when we do a decay test on our vacuum, which we'll talk about in just a second here. Now, some people will ask you, they'll say, well, wait a minute, that 1/4-inch fitting, isn't that going to slow the flow down? And the answer is absolutely not. That small 1/4-inch fitting will not have near the effect as the friction of the hose. What we're talking about now is conductance speed of a hose. And conductance speed simply is a measure of how fast we can move gas through a hose. The smaller the hose is, the higher the friction is in that hose. It's the same thing if we talk about undersized electrical conductors or undersized water pipes. If we're going to get the same flow out, it's either got to be at a higher pressure, right? Or we got to use a bigger hose. And we're talking about evacuation. When we get down into the below 1,000 micron range, we're talking about pressures that are 0.02, let's say, PSI. We're talking about tiny, tiny, tiny pressures. So in order to get that gas to move through that hose, we have to have a hose that has a very, very low resistance. And that low resistance comes from having a larger interior diameter and allowing that gas to more easily flow out of the hose. Do you have it up to there, Brian? So we're eliminating the manifold. We're connecting with 2 large diameter hoses from our core tools straight back to our vacuum pump, because the limiting factor of your vacuum pump is the what?
Diameter of the hoses.
Diameter of the hoses, right. And other restrictions that are in the system. Again, we talked about Schrader cores. Those are also huge restrictions in there, right?
Probably greater, right? I mean, Schrader cores are probably a greater restriction even than the hoses.
Actually,
right?
That is incorrect.
Okay.
A 1/4-inch hose is, I'll have to look at the math. You might be right. We'll do that as a video sometime. I'll do it with and without the Schrader cores, and we'll do 1/4-inch and 1/2-inch hoses to see which one's a bigger restriction. So it could be right, but I'm thinking actually the hoses play a bigger factor in this than the Schrader cores do, is what my gut tells me.
So the Schrader cores are a greater restriction in the traditional sense, meaning it's a smaller orifice, obviously, but by the time you take into account the length of the hose, that's what
it's the length and diameter that plays the biggest factor in evacuation. Here's the next dirty secret in evacuation. Everything leaks. Okay, hoses leak. Even copper leaks at a molecular level. It's such a low level we don't really care about it. I'd say for our purposes, we would say probably copper's leak free. It's as leak free as we're ever going to get for what we do. But everything leaks, especially hoses and especially evacuation manifolds or manifolds. We need to isolate those from the system. And that's what the core tools are for. So when you're attaching your vacuum rig and you want to use a core removal tool to attach your micron gauge to the side port, not to the end port, but to the side port to the core tool, okay? And you're going to connect your vacuum gauge with a brass connector or a copper connector. You don't want to use a hose in this case. What we're trying to do when we close those two core tools off, we're isolating the evacuation rig from the system, because that evacuation rig is made with rubber hoses and rubber gaskets and all kinds of things that leak. And luckily, the vacuum pump can overcome the leak rate of the hoses and still pull down the system, okay? But when we're doing a decay test, which means we've closed those core tools off and isolated the vacuum, what we're doing now is we're seeing what is the ultimate level of vacuum that's been attained. How deep is that vacuum? Is it maintaining that vacuum, once we've isolated? And, that's where you get into decay. And decay is simply when we isolate the vacuum pump, let's say it's down at 100 microns and we isolate it and it creeps up to 150 microns and then stabilizes, it's decayed 50 microns. All right. And that's okay. As long as we're below 500 microns, it's ideal. But you can't over evacuate a system. And again, you want to use those core tools to isolate it when you get down there. And literally, if you just pay attention to these couple things, large diameter hoses, remove the cores, attach it to your vacuum pump directly, you're going to cut your evacuation time down from hours to literally minutes. And we're talking a factor of 16 times faster. So, if you think about that 16 times faster, what's taken you an hour to do takes me a matter of minutes, right? That's a good thing. I'll tell you this, at the end of the day, some guys are going, I don't need all that stuff. I just go ahead and hook my vacuum gauge up and, sweat my copper first, get the line set, do the coil, and then, it can run for an hour, hour and a half, 2 hours. I don't care. I got other things to do on the job while I'm waiting for that vacuum pump to run. Well, a couple of things on that. Number one is, why do you want to wear out your pump? What's the point in letting the pump run all that long when you could be running that pump a much shorter time and getting the job done a whole heck of a lot faster? Number two is, how many times have you ended the job at 3:30, and 3:30 you go out there and you're going to go cut the charge and you figure out you got something going on, you got a leak in your system, you got moisture in the system, you got something going on there, and all of a sudden you realize, crud, now I got to wait around for another hour or 2 hours for that thing to evacuate, or now I got to blow nitrogen through and rebraze the thing and go all through this process and get everything out, where we could have figured that out way, way earlier in the process of the day, right? Because at the end of the day, we all know there's technicians that are going to say, you know what? 1,000's good enough. I'm cutting the gas in and I'm going, and that system's not going to last as long. There are advantages to being able to do stuff faster. And the big advantage is we don't have to waste time, especially when we don't want to waste time doing it. Just doing these couple things, you're going to find out very quickly it's going to take a lot of the pain, I think, out of the process as we go.
And one thing that I think techs miss, because my brother and I have this consistent argument where my brother is a great technician and he does things the right way the bulk of the time, but he has this argument with me about going direct to the pump and using larger hoses and all this, because I've always done it this way and it works okay. But I think the thing that you're missing, or a lot of technicians are missing, is that it's almost impossible to do a good decay test if you're doing it the traditional way. So let's say you even feel okay with how long it's taking. Well, first of all, you're not going to be able to get to leak detection as quickly. When I say leak detection, making sure that you don't have leaks or you don't have a wet system, you're not going to get to that decay test as quickly. And so you're going to find out later, too late, that you have an issue. But I think the reason why a lot of techs don't see the value in it is because they're not doing this test at all. So they're not doing the valve it off, see how it does test. They're literally pulling down to 500 microns. I'm down to 500 microns, shut it off, release the charge, move on, right? Or charge the system, move on. But you're missing a very important step, because you can pull down to 500 microns, say, and still have a wet system. And this is something that I didn't realize, I don't think, up until the last few years. Would you quickly just go into that? Like, what is wrong with the system where guys just pull down to 500 microns, shut off their gauges, release the charge?
All right. Well, first of all, let's talk about a couple things here, because I think people forget about some fundamental things. All right. Let's just talk about a return in a room. Okay? Or here, let's just do a better analogy here. If I gave you a straw and I set a birthday cake 2 foot in front of you, even a foot in front of you, and I gave you a straw and tell you, blow out that candle with the straw. Pretty easily done, right? You could blow that candle out, not a problem at all. Now, if I lit the candle again and I tell you now, suck the candle out with a straw. right? It'd be impossible. There's no way you could suck hard enough on the straw to suck the candle out. Well, why is that? Why can we blow a candle out, but we can't suck a candle out through the saw? Well, it all comes down to this, is that air in a vacuum pulls from a localized area. So you're not going to pull air across the room. You're not going to pull the air away from using that straw. You're not going to pull it from a foot away and suck that flame out off that candle. It's impossible because air is going to pull from a localized area. Now, understanding this is, again, another fundamental thing. Don't ever hook your vacuum gauge up at your vacuum pump. You're not measuring the pressure at the far end of the system. You're measuring the pressure at the vacuum pump. Again, it'd be like hooking your vacuum gauge up to the straw. Is there a negative pressure on the straw? Absolutely. Then why isn't the candle going out? Because there's no negative pressure at the candle, right? It's the same thing when we're pulling a vacuum. We have to be able to isolate the vacuum gauge from the pump to test the decay. In other words, to see how deep the vacuum actually is. Because the vacuum at the pump is not indicating how deep the vacuum is at the system, and especially at the far end of the system. Some guys will tell you, well, you need to sweat in a pressure port at the external equalizer in your TXV, or you need to have something inside to hook your vacuum gauge up inside. Yeah, that's a good way of doing it. It'll tell you that your vacuum in the house is getting to a certain depth, but that's exactly the same thing you're doing when you have core tools and you can isolate it, right? When you shut those two core tool valves, they're basically just ball valves. They're vacuum rated ball valves. When you close those ball valves off, what you're doing is you're allowing the vacuum to stabilize. You may see the vacuum go up a little. You may see the vacuum go down a little. The vacuum can do some crazy things, but it's stabilizing that vacuum in the system. And as that vacuum stabilizes in the system, what you're going to see is what Brian was talking about, which is the decay, which is how much different is the vacuum now than it was before I isolated the vacuum rig with my core tools. And we want to make sure that when we isolate it, it stays below the 500 microns. When you're reading 500 microns at the pump, you could be at 1,000 microns or even 2,000 microns if you're using quarter-inch hoses at the system. There is absolutely no guarantee that system is anywhere near dry enough when you're measuring vacuum at your pump. Why did they put that quarter-inch tap on top of the pump? Because marketing was running engineering, right? Because some guy's saying, well, I can't hook up with my hoses. I have quarter-inch hoses. I need to be able to attach a quarter-inch hose to my pump. Again, get rid of the quarter-inch hoses and cap that fitting off, because the only thing that fitting should be used for, the only thing, is testing the performance of your pump to see when you valve it off, how deep can your pump pull. And your pump should be able to pull down below 50 microns. Below 25 microns is ideal. It'll take a few minutes to get down there. Don't fret about that either. You can let it run for a few seconds. But that's about the only thing that fitting is actually used for. So when we isolate that vacuum from the system and it equalizes out, that's what the decay is, and that's where we want to see below 500 microns. If you're cutting it off too early, you're making a huge, huge mistake that's going to lead to a short life of that system.
Yeah, because also, let's say you have moisture in the system. I mean, Neil Comparetto just did a video about how you can even create ice in some lab conditions. Probably not a real practical thing in a normal system, but that can even occur, where he was pulling down below 500 microns and he actually had ice inside his little mason jar right there. You could see it. There was moisture there, and you could see on his gauge it said 500 microns. Because as water is evaporating, as it's boiling inside the system, if you do have any moisture in the system, that happens over time, and all that moisture isn't right there at your port. It's not like it happens instantaneously. It's a process. And so let's say you have some moisture that's in your compressor or in your evaporator coil or in your line set in a chaser or whatever, and you're pulling a vacuum, and the actual CFM at the pump itself has overcome that and pulled it down. Unless you valve it off and watch that decay rate, you're not going to know that you still have a wet system. Now, as soon as you valve it off, if you do have a wet system, it's going to go up a little bit at first, and then it's just going to keep rising. It's not going to stop rising until it gets up to the boiling point of water at that particular temperature.
You bring up another very important point. You're absolute genius. And that is this: there are no significant flows in a vacuum or during the evacuation process. And I want you to think about this one for a minute. A lot of guys think we're going to suck the water out of there. Does not happen. If you were to take and put a drop of water at the far end of a Coke bottle, all right, and then suck on that Coke bottle, no matter how hard you suck on that Coke bottle, that drop of water is not going to move. It's going to sit in that Coke bottle right at the bottom. You can't suck that drop of water out. It's absolutely impossible. So how does the vacuum pump remove it? Well, the vacuum pump lowers the pressure. And when it lowers the pressure, we lower the boiling point. And the heat that's in the bottle and in that water starts to cause it to boil violently, right? And it changes state. And as it's changing state, it absorbs heat from the bottle and absorbs heat from the water. And that water actually gets colder and colder as it goes. And so what you're going to see, if you were to actually measure the temperature of that drop of water, is as soon as you pull a vacuum on it, it starts to reduce in temperature because it's changing state. Well, as it reduces in temperature, it also reduces the amount of evaporation of that water. It starts to evaporate slower and slower because of the lower and lower temperature. So as we pull a vacuum on a system and we change the state of that water as it starts to boil away and absorbs heat, it's going to take longer and longer and longer to remove it because it's getting colder and colder and colder and colder, and it's not evaporating as fast. Now, eventually it gets so cold that it actually turns to ice. And the freezing point of water is 32 degrees. There's some science that says, it changes slightly under vacuum, but for all intents and purposes, at 32, that thing's freezing. Now the question becomes well, once it hits 32, does it continue to get colder? Well, is it changing state still? Absolutely. But at this point, we're changing from a solid directly to a gas because we're not evaporating anymore. We're sublimating at this point. The moisture has stopped boiling because it's frozen, and now we're changing directly from a solid to a gas. And then it takes a huge amount of time to remove that ice at this point from the system. Now, you stop and think about this for a minute, because does ice evaporate? Well, those of us that are old enough, I think Brian and I are, and probably some of the people listening will be old enough to remember ice cube trays in refrigerators. And ice cube trays, you'd pull out what looked like old ice, and it used to have all the edges rounded off, and the ice would have shrunk down, and it's like it evaporated, right? The ice actually evaporated, and you got these ice cubes that are these little tiny round, funky-looking ice cubes that also don't taste too good because they've sucked up flavor from the freezer. But those ice cubes are sublimated ice. They've actually evaporated away, and it's the same thing that happens in a vacuum. And just like it took weeks or months for that ice to evaporate in a refrigerator, it takes a huge amount of time also in a vacuum. But once you pull your initial vacuum, in other words, once you move that initial bit of atmosphere out, in seconds, in literally seconds, 90% of the atmosphere is gone. In a couple minutes, 99% of the atmosphere is gone. And, just think about this for just a minute. If you did the math, we've got 760,000 microns of atmospheric pressure. We're pulling it down to 500 microns. You're talking about fractions of a percent of atmosphere we're talking about removing. That has a huge impact on system performance. We got to get that out of there. Don't think because we got most of it out of there, it's done at this point. But that last little bit of moisture, that last little bit of ice, it takes a lot of time to remove if you get it in there. Now, the other thing Brian had mentioned was that we're not going to make ice except under the right conditions. Well, the right conditions are occurring all the time when, A, we evacuate a system in the winter or in the fall, or
True.
When we evacuate a refrigeration system that has a box that has multiple evaporators and is cold. Moisture will migrate to the coldest place in the system. So if there's moisture in the system, it's going to migrate into that cold evaporator, and it's going to sit there until we remove it with our vacuum pump. And because we have this cold evaporator, a good practice is to turn on the defrost heaters during the evacuation process to help warm that evaporator up to drive that moisture out of the evaporator, melt any ice that's in there. These are things that refrigeration guys deal with all the time. So we've got to make sure that our conditions right. Yeah, they can be. And they can be right for air conditioning technicians. They can be right for refrigeration technicians to make ice in a vacuum. And it absolutely does happen.
So here's what I was meaning to say, and I said that completely inaccurately. Thank you for pointing that out. What I meant to say was a lot of technicians now are using the creation of ice as a reason not to pull fast vacuums, not to do your evacuation quickly. So they're using that as an argument to say, well, don't use large diameter hoses. Don't do this stuff because if you pull your vacuum too quickly, it's going to cause you to form ice. And the cases in which pulling the vacuum quickly versus not quickly will cause ice to build up, that being the deciding factor, are very rare. It being due to the fact of ambient conditions being, below 32 degrees or near that temperature, that's very common. I mean, that will happen all the time.
It's not even a good argument because this is physics. This isn't magic. It's physics. And if we make ice, we can tell that with a vacuum gauge, especially if you use a high-quality vacuum gauge like the AccuTools vacuum gauge. It has high resolution and high accuracy that we can definitively tell the difference between moisture and just general pressure in the system. All you need to do if you get moisture in the system is break the vacuum with nitrogen, let it set a minute to warm back up, and then pull it down again. The key is warming that moisture back up. We talked about this earlier. Once you start pulling the vacuum, the water starts changing state and getting colder. Once it gets colder, it takes longer to remove. It doesn't matter whether it's quarter-inch hoses, half-inch hoses, whatever. Once it turns to ice, it even takes longer to remove. But if we break the vacuum with nitrogen, it's going to effectively do the same thing. It's going to have time to warm up, and then gases remove extremely fast out of a system. So when you put nitrogen back in the system, not going to hurt a thing. It's going to come down very quickly. When you have moisture in there, it's going to take time. And there's nothing more important than keeping your line sets clean and dry when you're doing your installation. Absolutely nothing more important. So you need to make sure that if you're not going to install that condenser, that those lines are capped off or soldered shut or brazed shut so that moisture cannot bond at a molecular level to that copper in there. Again, moisture will condense on cool surfaces, so it will condense inside copper tubing, and then it takes forever to get that system dried out. And then there's one more thing, Brian. I know we're coming up on the time here. I want to make sure that I cover one more thing that is really important that I think frustrates a lot of guys out there with vacuum gauges. And that is residual refrigerant in the system. Little experiment. Next time you get out your vacuum gauge, take a tank of gas and just take a tiny bit of refrigerant and just purge it into the tip of your micron gauge. Okay, and watch what happens. Exposing your vacuum gauge to refrigerant is going to make the vacuum gauge act erratically. It's going to make that gauge probably go down to 600, 3600, some kind of a micron range, really low. You're going to be surprised when you hit that with just a tiny bit of refrigerant vapor. Well, why is that? Well, vacuum gauges work off thermal conductivity, and air or nitrogen is what those gauges are typically calibrated for. Refrigerant has different thermal properties than air and nitrogen does, and it's going to affect the way the gauge reads. In a heavily refrigerant-laden atmosphere, the gauge is going to not read as accurately as it does once you get that refrigerant out. Now, realize that if you're taking a system that you've just recently serviced, like let's say you changed out a TXV and you're pulling the vacuum back down again, and there's refrigerant oil are miscible, and there's refrigerant boiling out of the oil in the compressor and out of the condenser and out of the piping and all that stuff. As you draw that vacuum down, there's less and less refrigerant in the system. You're basically degassing that system. It's going to be the same as if you had air in the system. In other words, well, the vacuum readings won't be the same at atmospheric pressure. As they come down, they're going to get closer and closer together because ultimately we're removing the atmosphere out, whether it's oxygen atmosphere, nitrogen atmosphere, or refrigerant atmosphere. Nitrogen and oxygen together, but please don't ever add oxygen to a refrigeration system or you'll kill yourself. Oil and oxygen do not mix. But as we pull this system down, as we pull this vacuum, they're getting closer and closer to the same. So sometimes what you have to do is you have to, if your vacuum gauge is seeming to stall, if you're getting erratic readings on your vacuum gauge, break the vacuum with nitrogen, and then let it set for a minute, and then start the evacuation again. That nitrogen will pull out some additional refrigerant with it, and it'll make the gauge start acting normal again. Sometimes you just get what's called a refrigerant-laden atmosphere. And the other thing you need to make sure of is that, for sure, I've seen this happen more times than one, your core tool needs to be fully opened by your brass connector on your vacuum gauge. That sometimes it happens where the core depressor is not out far enough, where it's not opening up the core depressor and the side port of the core tool. So you can either remove that thing out if you want to remove it out, because again, vacuum gauges like the AccuTools, one can handle up to 500 PSI, so you're really not going to hurt anything. Or you can, just make sure that the depressor is actually physically depressing it in far enough. But again, important note here, vacuum gauges are calibrated with either air or nitrogen, and if you're not in that atmosphere, it can affect the readings of your gauges. And a lot of guys don't realize that. And simply breaking the vacuum with a little nitrogen will resolve that issue when you start the evacuation again.
You kind of answered the question that I had. This is to my shame because I haven't looked this up myself, but you mentioned that the AccuTools micron gauge allows it to be pressurized. Are you aware of any micron gauges that have an issue if refrigerant pressure is applied? Because that comes up a lot. My technicians have asked, well, I'm done with my vacuum and now I need to release my charge or charge the unit. Am I safe to do that with the micron gauge still installed on the side port? Because obviously if they remove it from that Schrader, then you just lost your whole vacuum right there. Or basically, whatever you do, you're going to lose your vacuum if you change to that micron gauge configuration.
It depends on the vacuum gauge and the manufacturer. You really have to look at your manufacturer's literature and see. First of all, a couple of interesting notes. There's a good designed vacuum gauge only has one port on it. A lot of them you'll see dual ports on there, and they did that because technicians wanted to hook 2/4-inch hoses in line so they could have their vacuum gauge in line. Again, that goes back to marketing, working for engineering. Not a good idea. You want to...
Oh, man. On those initial subcodes, that was another thing they did, is everybody was trying to pull through them, and it was horrible. I mean, it didn't work at all.
It absolutely will not work. And then you're really going to contaminate your gauge, especially if you put refrigerant or oil or anything through there. It's a nightmare. So even if you have a gauge that's got dual ports on there, cap one of them off and connect the other one directly to the side port of your core tool. That said, there's no flow into that thing. Right? As soon as you release refrigerant in there, the pressure's only going to go part way up the stem, and then it's going to sort of stop going into your vacuum gauge because there's no outlet. If there's no place for the gas to get out, it really can't get in and contaminate that sensor in there. So don't worry about subjecting that to a little bit of pressure. It's not going to hurt anything. But you have to see how your manufacturer rates that vacuum gauge, because some of them will not handle pressure at all. You know, like the old thermal engineering ones, they'd handle about 30 to 50 pounds of pressure on there. And if you got anything higher than that, you're going to, blow the back end of the unit out because it's not a pressure rated device. Realistically, when I'm doing an evacuation, what I do is I usually connect to the liquid side of the system and I very slowly crack open my suction service valve and pressurize the system very slowly. And when it gets up to 1 or 2 PSI, I'll take the gauge off, because at that point, what I'm trying to do is just make sure that I've got enough pressure on the system that I can actually know it's above atmospheric pressure. I'll take my gauge off the system and then go from there. It really depends on the manufacturer. Here's one thing to close with. Think about this for just a second. How many of you guys have had somebody out to service your refrigerator? I would care to say it's almost none of you. Right? If your refrigerator doesn't work, how many of you guys would run out real quick and get some piercing valves and throw them on there and check the charge? My guess is none of you, right? Well, why does that refrigeration system run for 20 years? Why can it run for 20 years sitting in your garage, chugging away, keeping your beer cold, but we can't make an air conditioner last for 1 or 2 years, sometimes without a breakdown? And it's because it was factory evacuated and charged, and it was done in a way that was correct. And if we do proper evacuation and charge, in my opinion, if you do it right once, you should never even check the charge again on that system. There's no reason to ever put gauges on that system again, because the refrigerant should never leak out. The only time we need to connect gauges is when we have a leak, and this is a whole other discussion, but think about this for just a minute. Units can run for 20 years. Air conditioning, P-Tech units, window units, whatever. All of us have worked on that stuff. How come that stuff can last forever, but our stuff doesn't? And it all comes down to because they did the job right. And if we start to do the job right, we're going to see exactly the same things. Important things to think about as you move forward.
Just attaching and removing gauges all the time is not a particularly good thing to be doing. You have the potential of adding in air and moisture every single time you do that if you don't purge your hoses. You want to talk about a shoot by the hip procedure. Purging hoses is probably the most, just haphazard thing that we do. We're just kind of, okay, that's about right. And then you move on. It's not a great practice that we have, but it's what we have to rely on. But we're going to come to a day where all the sensors are going to be inside the unit, or a majority of them, and we can do it right the first time, and then we can just monitor without having to connect and disconnect, which is a future that I like. I think some guys might be scared of it.
I think, again, that's craziness, right? Because I haven't had a pressure transducer in my refrigerator since I've been a kid, and I've never needed to know what the pressure is in the refrigerator. It just keeps working. And that's stuff we don't need to add. We don't need to know pressures, temperatures, superheat, subcooling. Once the thing is charged and charged correctly, the biggest part of our job is removing dirt. Keep the evaporator clean, keep the condenser clean, keep the compressor clean around that, check electrical components. Do we need to know that information? No, we really don't. It's not, once the charge is right, it pretty much stays right. And we will always, always, always need field equipment to test stationary equipment. We've had stationary stuff forever in factories and in industry, and all that stationary equipment has to go through periodic calibrations and tests to make sure that it's accurate. And putting a pressure transducer in a system and expecting it to last 20 years is ridiculous. It's under a huge amount of duty all the time. And while these things, again, they sound good and they sound like great solutions, do we really need them? I say no. So
forget I ever brought up the transducer thing.
Yeah,
then.
well,
Just forget it.
Hey, we're seeing equipment come out. I just saw some new, I want to say it was York, maybe came out with a new unit that gives you all that information.
The Carrier Infinity has been giving us that for years. I mean, the one in my house, I just go look at the thermostat and it tells me most of this information. It doesn't give me subcool, strangely enough, but it gives superheat and pressures. And
yeah, it's cool. It's cool stuff
anyway.
for sure. I mean, it's cool stuff, but again, it goes down to if you don't know what it should be, what difference does it make what it is, right? If we're gonna make measurements without knowledge, what difference does it make what they are? It is what it is. It's a function of the load. So having that at our fingertips is only as good as the other information we have at our fingertips to know what that reading should be. All right. Well, why don't we get this one wrapped up, Brian? And I look forward to talking to you in the next one.
All right. Sounds good. Thanks, Jim.
All right.
All right. Well, thank you for listening all the way to the end. If you haven't subscribed to this podcast on a podcast app on your phone, then you're really missing out. If you have an iPhone, you already have a podcast app right on your phone. You can subscribe there by just typing in HVAC. If you have an Android phone, you can download the Stitcher app and search HVAC and do the same thing. Subscribe there. One thing that I wanted to mention here, just because it's very pertinent to this conversation, is a lot of people think like I'm a big proponent of digital gauges, and I am, but I haven't always been, and actually I very much prefer analog gauges. I know this is sort of a, like, what is Brian talking about this for? But I wanted to just bring this up because whenever we talk about evacuation, one thing that I think we can easily miss is the practices before evacuation, which is nitrogen pressurization, and then also breaking your vacuum with nitrogen. But specifically when you're first doing your pressure test, you want to make sure that you don't have any leaks before you go into vacuum. And one thing that I found since we've started using digital, specifically either the Testo Smart Probes, Testo 550 or Testo 557, those are the three that we use in the business, what we're finding is we're having much fewer leaks because when we pressurize up to, say, 300 psi, when we're doing our standing pressure test, we're able to see very small changes on the digital gauge that we may have missed previously with the analog. So that's one thing that I want to just sort of mention in general is digital gauges, high resolution digital gauges can help you find leaks before you go into vacuum, which can help save you a lot of time because you don't really want to be finding out that you have leaks in vacuum because then you're pulling moisture in, you're pulling air in, not a good thing. And so a good set of digital gauges can help you with that. Many of you know that I sort of partner with TruTech Tools. It really is just as simple as I met Bill, and I really believe in TruTech. I believe that they support the product really well. And so Bill gave us an offer code, which is GetSchooled, all one word. So if you want to look at a good set of digital manifolds, I would suggest that you go to TruTechTools.com, have a look there. You'll find that their prices are very competitive, but even more than that, they really, really support their products. And they're a company that really supports the industries with training and help and just does a lot of good things. So I would encourage you to look at that. And then also, as always, pull a good vacuum and keep your system dry. Until next time on HVAC School.